Alrighty, so I want to talk really quickly about displacement and velocity graphs. Now, a displacement function, let's call it x of t, has two inputs. It has one input and one output. The t variable is our time, and our x is our distance. Now we can imagine it in a more simple position, like thinking about a graph. Now imagine that we have a ball sitting on the ground, and then it is kicked up and down. On this axis, we're measuring t, the time in seconds, and over here we're measuring the distance, which we're going to call x, which is the distance above the ground. Alrighty, and as you can see, this, is looking like some kind of quadratic, right? Poorly drawn one, but you can see it's some kind of quadratic. Now, what you can think about is, well, what is the rate of change, or the derivative, the slope? How can we interpret that? Well, the slope is a rate of change, right? What's the rate of change when we have meters and seconds? Well, the rate of change could be approximated by just finding an average change in x, an average distance, and for a given amount of time. So a small change of x for a small change of t, a small change of distance over a small change of time. Well, what would that be measured in? Well, x is being measured in meters, and time is being measured in seconds, so it'd be measured in meters per second. So when we think about the true rate of change, which is once we take that limit as h goes to 0, the absolute one, well, the rate of change would be dx dt, and this would be equivalent to the speed, right? Speed in meters per second. Meters per second is a speed measurement. And we see that if we have a displacement function, x of t, then dx of t would be equal to a speed function, which we could call s of t. So what that says is that the x dash of t could be equal to the speed of t, or dx dt is equal to the speed function. Alrighty, let's have a look at an application. So we've got this particle moving in a horizontal line such that the position x meters relative to a fixed origin O at time s is given by x of t is equal to minus 3 t minus 1 squared plus 12 for t positive. Sketch the displacement time graph showing all key features. Alrighty, so first of all, let's notice that it's quadratic and it's in turning point form, which means that the turning point is going to be 112. So that's really easy to figure out. Next thing, let's think about the t-intercept, which is going to be when x is equal to 0. Alrighty, so we're going to get 0 is equal to minus 3 t minus 1 squared plus 12. Now this is quite easily solvable because in root form we just rearrange. So minus 12 is equal to minus 3 t minus 1. Divide both sides by negative 3. Take the square root, remembering the plus or minus. And so we get 1 plus or minus 2 is the value of t. Or we can think about that as t is equal to 3, or t is equal to minus 1. Now minus 1 is out. Why? Because we were given a domain. The domain is that t has to be positive. So we've only got one t-intercept, which is going to be at t equals 3. Let's think about our x-intercept. Our x-intercept is going to be when t is equal to 0, and so we can just directly substitute that in. Alrighty, minus 1 squared is positive 1, minus 3 plus 12 is 9. And so we've got our x-intercept at 9, we've got a turning point, and we've got one of our two intercepts that we need. So let's do a sketch. So we've got t down here on the x-axis, and we've got x of t on the y-axis. Now, it starts at a value of 9, it goes up to a value of 12, and it hits the ground over here at 3. And we can draw in our quadratic nicely there. Alrighty, so that is part A all done. We finished up our sketch. Alrighty, let's have a look at B. Determine the distance the particle has travelled when it had reached the origin and describe the journey taken. Alrighty, so first of all, it went 3 meters up and then it went 12 meters down. Alright, so it went 3 meters up, 12 meters down, so a total of 15 meters, so it travelled 3 up and 12 down. In terms of the actual thing, it's actually moving horizontally. So we might think instead of up and down, we could do right and left. Alrighty. So total distance was 15. Alrighty. Determine the particle's maximum velocity. Well, the velocity function v of t is going to be equal to the derivative of x, as we said before. So the derivative of displacement is velocity. So let's substitute in the function and take the derivative. So first of all, we might want to expand out x of t. Alrighty, so let's expand out the brackets. Expand out the next brackets. And collect like terms. And now that we've got this function, we can now take the derivative of it. So we're going to get minus 6t plus 6. And remember, we're only interested still when t is greater or equal to 0. So we can think about this function here. This is just a linear function, right? Minus 6t plus 6. It's a decreasing one. It's got a negative gradient. So when's the highest point? Well, the highest point of any linear function that's decreasing, right, is the leftmost point, for it's going to constantly be getting lower the further right you go. So, therefore, the fastest velocity is going to be when t is equal to 0. V of 0, which is equal to 6, which is 6, in this case, meters per second. That's the fastest velocity that you're going to get. You can also see it on the graph, right? That's the steepest point it's going up, and then it slowly slows down until it's flat, and then it begins to decrease, right? And at the point it's decreasing, the speed, the rate of change, is going to be negative. Alrighty, last part to go. Determine the particle's velocity at t equals 2. Alrighty, so v of t is equal to minus 6t plus 6, and we're interested when t is equal to 2. V of 2 is equal to minus 6, 2 plus 6, which is going to be minus 6. Now, velocity is a measure of speed, which is meters per second. So therefore, the function, the particle is moving at at 6 meters per perspective towards the origin after 2 seconds. Alrighty, so that's the end of the question, and I'll see you in the next one. Alrighty, bye-bye.